just a very brief overview of what is crystal plasticity finite element method. So crystal plasticity finite element method is similar to any other finite element method, which actually you discretize a body and you solve a boundary value problem. In this case, the FE solver will provide you the meso deformation gradients and nodal displacement, basically, which you can process and get the deformation gradients at the integration point. This is where the crystal plasticity comes into the play, and it solves the constitutive model at the integration level. And it calculates for you the mesoscale stress and consistent tangent modulus out of that meso calculation, and it pass it back to the finite element software for another round of iteration. So that's pretty much very close to finite element. Many concepts still remain valid, except at the integration point level, constitutive model is controlled by continuum slip theory and crystal plasticity. So what is PRISM's plasticity code and what are the capabilities it has? So it has both rate dependent and rate independent crystal plasticity models. There are different twinning models you can use. It has both isotropic and kinematic hardening. It can be easily connected to preprocessors like Nepper and Dream3D, which is specifically, I'll go over Dream3D connection today. It can be easily integrated with materials commons, and it has a really good scaling. That's one of the biggest advantage of using PRISM's plasticity. It can handle multi-phase problem. You can add effect of grain size. It has a very simple input file. I'll go over it today so you get familiar with most of the features. And it has a detailed online user guide and application to get you started. It has also YouTube videos that for very basic applications, it can get you started, and also for installation and some of the post-processing as well. And it's highly modular. So if you are kind of developer and want to add your feature, you don't have to mess up with the whole code. There's specific files for each action that you can just modify those. Specifically, if you have your own crystal plasticity model and you feel comfortable with that, it's pretty simple. You just need to modify one file and it's in C++. So you can, if you have other languages, it's fairly easy if you are a developer to translate that file to the calculate plasticity we have in PRISM's plasticity, which I will go over this feature a little bit on training sessions number 2, which is kind of an advanced feature. And one more theoretical slide. Why does someone actually want to use PRISM's plasticity as its crystal plastified element solver? There are two benefits in using that. First one, you don't have any licenses for that, especially like if you go to commercial software like Abacus, ANSYS, you have to pay. On top of that, if you want to do parallel simulation, you need to pay for multiple licenses. That's one. But on top of that, even if you're working in a university and you're interested in doing larger scale simulation, that's actually another big benefit that PRISM's plasticity comes into play. As you can see, we did a scaling study, PRISM's plasticity versus Abacus. And for a sample with 7,500 grains, with about 700,000 elements, we compared the simulation time for cyclic loading. And to reach the first compression, Abacus required 28.5 hours. It's more than a day to finish the simulation, while PRISM's plasticity just require 1 hour. Both of the simulation has compared on about 480 processors. So in the curve of scaling, you can see after 300 something, or even slower, even lower number of processors, Abacus start to make a plateau, which means it doesn't matter if you actually use more processors to solve this problem. But in PRISM's plasticity, you still get efficiency after you increase the number of processors. Look, this is like 700,000 elements and with crystal plasticity solver. All the assumptions are pretty much the same within this comparison, but we tried even larger sample. Abacus could not handle very well a very large sample within the number of elements, like in the order of more than 1 million with hex elements. It's really hard to handle that simulation with Abacus. And in some of our study, we actually did about 16 million elements with PRISMS-Plasticity. So it gives you a lot of flexibility, and it's open source. So you can actually go and see the code and change any feature you want. And within the commercial software, it's not that feasible. You can have a limited access to some of the applications or source codes. So the first thing I want to explain is how you can actually get some information. So if you go on the Google, let me actually switch back the handout with this. If you can actually Google Prism Center Plasticity GitHub, there's a link. You can click on that. It's a GitHub repository of PRISMS-Plasticity. So you can clone the latest version. You can see the older version, and you can follow the update and installation by watching or starring it. So whatever feature we update about the code, if you follow it, actually it will automatically send you an email that, hey, this feature is added to the code. So that's the first thing. Again, you can see some general information about the code, the link to the YouTubes, how you can install it. So there are a few folders. I'm gonna go over it right now. So the first one is training materials. There are really useful tools here that I'm gonna go over them today. One of them is post-processing. The other one is pre-processing. So each one of these folders contain some useful information regarding using PRISMS-Plasticity. The next folder is applications. If you click on Crystal Plasticity, there are different applications that can get you started. You can, after maybe today's session, it's really a good idea to go over some of these applications and compile them and run them and make some changes to get comfortable with the results. Another important folder is docs. Some of the important documentations are shared here. We tried our best to update them. Maybe you can find a small little bit of information that has not been updated, but it's pretty much, we tried our best to keep this updated. This user manual is our master user, so it will go over most of the detail you have in the input file, how you can change it, and whatever new feature we added to the code, we try to come up with a clarification in this user manual. In other words, the other one is installation. Another one is if you want to implement your own constitutive model, what actions you need to take, and along this user-defined material model manual. And this is pretty much most of the important feature you can find in documentation. And in the source, you can find most of the source codes of the codes that if you want to make any advanced changes, you can change here and then recompile it and use it. And include folder has the headers. So these are the pretty much important folders in the GitHub repository. But the first example that I'm gonna do, I'm just gonna show you the files. Here it's application, Crystal Plasticity. In the handout, I put FCC compression. The sample that I actually solved was FCC random orientation block, which is a random orientation FCC copper sample during compression. So you can see there are 6 files or 6 master input files here. The most important one is this one, prm.prm, which is the main input file. I'll go over this after I give you some idea about the pre-processing. The next one is grain ID and orientation, which these define your macrostructure simulated with PRISMS-Plasticity. The boundary condition.txt define the boundary condition you're applying to the sample, the latent hardening ratio.txt define the interaction between different sleep and twin system, how they actually get hardened as another pair of sleep system get activated. And the last one is sleep normal and sleep direction. An extra file you can have here, set of files you can have here is twin directions and twin normals. In the case you have a sample macrostructure with twinning is important. So after that, the next step, if you go to the page number 6, which is actually here, we're gonna go over how you can generate a macrostructure using Dream 3D for PRISMS-Plasticity. So to do that, first I need to open the Dream 3D executive. So if you have the Dream 3D folder, you can see there is a Dream 3D icon here. And if you open it, hopefully it will open the Dream 3D pipeline. Now you need to go here, File, Open. So if you are using Ubuntu or Windows, it doesn't matter. If you git clone the PRISMS-Plasticity, you can get the training materials here, pre-processing here, in this case HCP. There is a file, Prisms Pipeline HCP. So you need to open Prisms Pipeline HCP. If you open this pipeline, so this is the folder, training plasticity, training materials, pre-processing HCP. There is a JSON pipeline which we made before. This pipeline, if you double click on it, it takes a minute to come up. If something, okay, good. So this, we actually prepared it for you. So it simply generates the macrostructure information you need, which are those two files, orientations, txt, and excuse me, the orientation txt and grain ID. So we'll go over this one by one to see what are the features. So if you go to the page 7 of handout, it's macrostructure generation. So it will have the features that I'm going to explain. So the first item on this pipeline is stat generator, which you can define the statistical information regarding the crystal structure, grain size, orientation, and the shape here. So everything can be modified here. For today's session, so here the important phase that I'm going to actually explain is, first you need to define the crystal structure. So if you click on this gear, here you have below the parameters, if you click on this gear, a box will show up. There you can select crystal structure. So if you click on that gear below parameters, you will have this box opened, and then because I'm trying to simulate the copper, I'll just pick cubic, and I remain this phase name to copper, and then click on OK. The next one is orientation. To define the texture of the macrostructure you're actually trying to generate, if you click on this ODF bottom, this is pretty much you need to define the texture. If you have an EBSD experimental file, you need to click on this bulk load from file, and then click on select and choose your file and define Euler space. It could be Quatronian and Rodriguez, and it's space, tab, dot, whatever delimiter you want to choose. And you can delete, you can choose values are in degrees or values are in radians. So for today's session, we just want to go with the random microstructure. So if you choose primary equiax, it will choose random texture. And these are the pole figures. So first, you need to refresh this. If you refresh this, because our crystal structure is FCC, you can see that. And let's make this horizontal and refresh this again. Okay. So this is the pole figure for copper for FCC material. So these are 01, 011, and 111.
Here, sir.
Yep.
Yeah, you can change the type from discrete to Lambert and refresh it. So then it'll show the colors as well.
Okay. Thank you, Adi. Okay, yeah, you're right.
Yeah, now this.
Okay, thank you. So then you can click on create data. And this will generate that sample for you with random texture. Now, if you go to your next page on the handout, the one after that, it's page 9, you can see if you have an eBSD file and you want to, let me bring it here. So if you have an eBSD file and you want to use that to define the texture, this is the format you need to change for Dream 3D. So it has first line, the angle count, it's a number of grain. Then it has 5 columns. And then these 3 are radians for eBSD grain orientation. And these 1 and 1 are weights that I just keep it as 1 to make it simple. So if you have an eBSD with the grain numbers and grain orientations, you can just add 2 columns of 1, and then eBSD, this would be your eBSD input file for bulk load from file. So you have to need this first line as an angle count and then orientation. You should keep this format if you want to get a valid. If you change anything here, like delete the first line or come up with another combination, when you actually went back to Dream 3D here, it will give you an error after bulk load. So in the next step, let me check everything. Okay. In the next step, if you go to the next page, there are pipelines number 8, 9, and 17. You actually need to change the address from the default, so you know where the microstructure generated from Dream 3D would be imported. So we're gonna go 8. We're gonna click on this. Let me see which folder. Training material, plasticity. Okay, this is good. So I'm gonna keep it. So grain ID. I might have a previous grain ID there. So I said, yes, replace it. And then I will go to the number 9, select it. And then I will change the name to copper and then save. And then number 17 as well, I will change it to HCP. Select the folder. And yep, that's it. So just to make sure that we don't mess up anything, I just click on this create data again to make sure that nothing has been. Okay. So if you have the, okay. The handout here. So this is the, then if you just click on the, something is messed up here. So I said reset. Okay. And then cubic. and then random, so create data. Okay, you're ready. Now that you have all the addresses update, you can just click on the start pipeline. So the feature numbers is, you can see, too much. So there is an important point you need to recover. So if you cancel the pipeline, if you go to stat generator, the first part, the size distribution, you can see that there is an initial synthetic file. There is an estimate number of features. So if you click on that, the estimate number of features are a lot. So you can just increase the grain average to 5. Okay, now it's better. And create the data. And if you go back to this, you can see that the estimate primary features are now 25. So the dimension is the number of voxel you will have. So if you have 32 by 32 by 32, Dream 3D will give you a voxelized mesh. So 32 by 32 by 32 will be your different dimension. So if you increase that to 50 by 50 by 50, it will be estimate primary features. You will have about 100 grains. Now, if you start pipeline, you can see that it will be really fast because the number of grains is now way smaller. Now let's go and check the files which has been generated by Dream 3D. So if you go and click on the plasticity, training materials, pre-processing, HCP, and then, okay, so here are the files. So if you go to the next page, this is the orientation.txt. So let's open orientation.txt. So in our case, it has 100 grain about. So you can see it's 97 grains. That's an estimate number of features. So it's not exact. So if you want to go over more details, here is the first row is dummy. So it doesn't matter actually. After that, it will give you 4 different columns. The first column is grain ID, and the next 3 are Rodriguez vector. So the Rodriguez vector, it can be defined in Euler angle in other codes. So you need to change it at the end in the orientation file to the Rodriguez vector, which are 3 components. So something is, this file is just number of grain ID and 4 columns. So the question is, what else can be added to orientations.txt? There are 2 more important features. First one is, if you have multi-phase simulation, for each feature, you need to define the phase ID as a 5th column. But there is another feature which is actually very useful. If you have some grain level data that it's different, like eigenstrain or the size of the grain or some other information that you want to pass to the code, you can actually add another column to these orientations or several columns as additional voxel info, and you can easily read in that into the software. So you can have any other grain level information imported to the code using orientation.txt. So if you go to page 12, it's grain ID.txt. So if you open the grain ID.txt, the first 20 lines are the headers. Then you will end up with 50 by 50 by 50. This is the voxelized size of the code. But we have a 3D matrix or array that you want to map it to a 2D matrix. So what we did is we used the Dream 3D convention for that, for PRISMS-Plasticity, to make it easier. the way it works is the first grain ID is for if you have a 3D, imagine if you have a 3D cube and it has small voxels, then you can index each of those with I, J, and K, which I, J, K 0 or 1, depending on what number you're starting, is the one at X, Y, and 0 equal to 0. After that, if you want to increase it, for example, let's go to I1, J1, and K1 and move it in X, Y, and Z, then you want to know which of this number is belong to that. Then you can see in the PDF handout that it would be J plus I minus 1 times N2 for a sample which has N1 times N2 times N3 voxels in X, Y, and Z direction. It's a little bit tricky, but I'll go over it after the training session if anyone's interested to know more about this convention. But it doesn't matter because Dream 3D will automatically generate the file for you, so you're fine. The next file is actually the Dream 3D will provide for you is a XDMF file that you can open with Paraview. So to open the Paraview, you can just download it with the link I sent and then go to bin and find this Paraview bottom. So close. Okay, it will take a minute to come. Okay. Okay, it comes up. So then you can actually open that XDMF file. So we go here. You find your folder. Okay, it's here. So it's plasticity, then training materials, pre-processing, HCP, copper XDMF. So if you double click on that, it will ask you 3 options. Just choose the one that it has been already selected, XDMF3 Reader S, and click on OK. Then you need to click on this apply. It will bring the outline. Then you can change the solid color to feature ID for grain IDs and make this outline surface with edges or surface. So this is the macro structure we generated with Dream 3D. So you can see this is the voxelized macro structure, and this is the basically X, Y, and Z equal to 1, IJK equal to 1. So this, if you want to know, for example, this, the grain ID of this one, then you can actually, let me see how I can, okay, I think this would maybe be helpful. And then, there was a view, memory inspector, nope. I don't, here we go. So if you go on the cell label, feature ID, you can see that, let me zoom in a little bit. And then, okay. So it's 26. No, it should be a cell label ID. So this will be this one should work. Okay. So this is cell numbers, feature ID. Okay, this is 62. So the feature is 62. And if you open the grain ID text that we had here, it's 62. So you can check with this that how your grain ID is actually changing. Okay, so this is the end of the part of how we can generate the macro structure using Dream 3D. So let's see if we have any question in the chat box. Okay, so we're good so far. So if there is any question regarding this section, that's a good time to ask. Okay, so we're gonna move on. So the next part is, how we do we determine the size of mesh here for crystal plastified element? No, we don't define the size of the mesh here for CPFEM. We actually define it in the main input file. Okay, sure. So the next part is we're gonna actually go over the input file we have and check all the boxes. So here are some, in page 14, some useful terminal command for Linux if you want to have a cheat sheet. And these are pretty common commands in Ubuntu. And this is pretty much what you need to do for the compiling PRISMS-Plasticity. So we'll do that together. Hopefully you have the DL2 installed in your Ubuntu or Windows submachine. So I'm using Windows submachine for today because I want to be handy going back and forth with Windows. So the first thing is, let's go to, I have my folder for today's training here. Okay. Okay. So I have already git cloned the PRISM-Plasticity, but let's get a fresh version just for the sake of today's session. So first, I'm generating a new folder test, and then I'm going to that folder. So this is an empty folder. So let's start to copy and paste some of the commands. So the first one is get clone the prisms get from the GitHub. So if you just copy and paste this, okay, or you can just type git clone Prism Center plasticity .git. Hopefully I didn't misspell anything. Oh, I did. Okay. Okay, there we go. So it's cloning the plasticity GitHub. Okay, we had a misspell, but it automatically figured that out. And then, I mean, an easier way to do that is actually open the plasticity folder and then copy it from here and then git clone this. That's the easier way to paste it directly. So now we have the plasticity folder. If you go to the plasticity folder, now you can do cmake dot. It will take maybe 15 seconds. And then you can do make -j 8 or 6. I'm using 6 processors. So this will compile the main source codes for PRISMS-Plasticity. After this, there will be one more step. So let's go back to the handout. We did this, we did CD plasticity, we did cmake dot, we did make -j. Instead of number of cores, you can put the number of processors you have. So we're now waiting for the PRISMS-Plasticity to be finished. So this will take typically 3 to 4 minutes. But while we are waiting for this, we are going to go over the file of the folder using another node editor. So this is pretty much the folders of plasticity that we just get cloned. If you go to application, if you go to crystal plasticity, if you go to FCC, we're gonna simulate this sample, FCC random orientation block. If you double click on that, these are the main input file that I explained it a little bit earlier. So the main file that I'm going to over is PRM. So you can either open it in the Ubuntu Linux using VIM or other text editor that you feel comfortable, or you can open it with Atom-I. I'm preferring that. So I'm opening with Atom. So this is the main input file we have. Okay. So this is basically where you define most of the controlling parameters for PRISMS-Plasticity. I'm going to go over most of these features while we are waiting for this compiling to finish. So if you go to your handout, in handouts, okay, let me check. Handout is, okay. So yep, the next one is going over the main input file, prm.prm. So let me go over them one by one. So the first part is FE parameters. This set order of find element define what's the order of find element you're using. For example, if you want to use linear hex element, higher order hex element, that defines that aspect in the FE simulation. The next one is order of quadrature. Here, the order of quadrature is 2. You can have reduced order of integration, which is then you need to pick 1. For order of quadrature point number 2, you will end up with 8 quadrature point in 3D. And for which is sufficient to integrate a linear hex element. The next part is domain parameters. So number of dimension, the PRISMS-Plasticity code is working only for 3D applications. So you always keep this 3. The next part is if you have a, assuming the simulation domain as a cuboid for arbitrary dimension, you can have in the X, Y, and Z direction, the size of the simulation box. So in this case, we are using a very simple cube with the unit length, which has like the length of X, Y, and Z is equal to 1. Okay, let's see if, okay, we are halfway through. So the next part is mesh parameters. So if you go to the next page on page 17 of your handout, the mesh parameters is very interesting. There are 2 ways you can refine your mesh. First one is defining subdivisions in the X, Y, and Z. For example, if you have So initially you have a sample with just one master element. If you define the subdivision X, Y, and Z, for example, in this case, 5 and 8 and 10, this is a 5 by 8 by 10 simulation FE mesh. So if I change that to 5, 8, and 5, then it becomes 5, 8, and by 5 FE mesh in the X, Y, and Z respectively. There is another feature which set refine factor. For each of those coarse mesh that you just generated using set subdivision X, Y, and Z, you can refine that by adding a point in the center of that element. For example, now with the set refine factor of 0, we have the FE discretization of 5 by 8 by 10. If you make the refine factor 1, each of those elements becomes, so if you make it 1, each of these elements becomes 4. So then you will have extra. For example, if you make the set refine factor of 2, each of those elements will be, in your case, in the handout, you have 2 by 2 by 2. If you make the set refine factor of 2, each of those becomes 4 smaller elements. So in each direction, you'll end up with 8 by 8 by 8 element. In this case, if I add set refine factor of 1, then it becomes 10 by 16 by 20, so on and so forth. So every time you're adding set refine factor, you're actually multiplying the whole number of elements by a factor of 8, which is 2 in each direction. Another feature which is not used here, but is explained in the handout is, there are 2 important points that I put in handout, is if either you are using periodic boundary condition or you're using grain ID deletion, these 2 features, you cannot have set refine factor larger than 0. So essentially, you need to discretize the whole sample using subdivisions. That's an important. If you just use set refine factor, the program will shoot you an error. So that's one important feature. On top of that, if you go on the next page of handout, you can use external mesh generation. So you can add these 2 lines, set use external mesh equal to true, and then name of the file that you have, that you need to have that file within the same folder. And there is an important part, which is external mesh parameter. What does this external mesh parameter do? So if you read in the external mesh from another mesh generator and not generated by DIL2 itself, then you might have round-off error on your boundaries. For example, when DIL2 generates the mesh, it's precise. So you have from 0 to 1, if you define the node on one face to get loaded, then there is no round-off error. So you don't need to have any limit for the uncertainty for applying that boundary condition. But when you're reading an external mesh, imagine instead of 1, you have 0.999. Then you need to have a certain region that say, hey, if the node is within that window of 1 plus minus that round of error, then it's still considered as the boundary node. And that region or round of error can be decided by this number, 0.05, multiplied by the domain size. So is this a relative factor? That's just to make sure. So you need to make sure that this number is not large, because if it's large, it actually engage other points which are not on the boundary and assume they are on the boundary. So you need to be very careful about this. But usually a number about, I would select 0.01, and it's basically, or maybe it's smaller. So you need to be careful. You need to simulate and get this parameter optimized depending on the round-off error of your mesh generator tool. So if we go back to the, okay, so the first part is done. Now we go CD, applications, crystal plasticity. So this is the crystal plasticity application part. So we do CMake dot It will take about 50 seconds for this part. And if you don't want to have a debug mode and you just want to have a release mode, you can then just use make release. So this will take another 50 seconds. Okay, while this is finishing, I'm just going to keep working on the. So after we are done with the mesh, the next part is output. So you're doing the simulation and you want to know what kind of output you want to plot. There are 3 types of output at least you can generate using PRISMS-Plasticity. One, stress strain, which is a macro homogenized response of the simulation. It's like an average stress strain information for each component. Another one is the variation on the sample, which can be opened using a Paraview, which generating PVTU or VTU output for you. It's like stress, strain. If you want to have a contour of effective strain or grain ID or whatever, you can just do that. This, excuse me, set right output, when it's false, it actually says you don't have that. But if you want to make it true, then you can actually will generating that output for you. This define which folder this will be generated to, and this define how many time step, how frequent the code will generate that output for you. In this case, it's like 100,000, very large, so it's not much. But if you make it 100, then every 100 time step, the code will generate that output for you. And this is pretty much defining if you want to have equivalent stress, strain, grain ID, or twin fraction outputted for you. Now, there is a feature. What else you want? For example, you want to sigma XX or strain ZX to be outputted as a contour plot so you can further analyze it in Paraview. There is an advanced feature for that I'm going to go over that on session 2. So keep that in mind that you can actually add features to this for your visualization. These are the pretty basic features. And next one is quadrature output. So if you add 2 lines of set quadrature output, let me bring the hands up. Okay, so this will be here. So if you add set right quadrature output true and set skip output steps, this will help you to generate the information for each quadrature input, for each quadrature point. So what does it provide for you? For example, you want to know for a specific region of quadrature points, you want to study statistical analysis, you want to post-process that data. So you need to provide that information. By default, there are a certain set of parameters that can be, that if you just turn this 2 feature true and skip output on, then you will generate a quadrature output with many variables. It actually, these are the type of information it will provide for you. Grain ID, phase ID, determinant of Jacobian, which is the element size divided by 8. If it's twinned or not, X, Y, and Z of the orientations, rotations of the updated rotations or Rodriguez vectors of that integration points, component of deformation gradient, elastic, plastic, so on and so forth. What if you don't want to output so many parameters? What if the size of the simulation is so large that you want to selectively output some specific information for your quadrature point? Then you need to actually open a file, which is if you have here, 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 there is a source file. If you go click on source, material models, crystal plasticity, there is a file, update after increment. If you open update after increment, And then you go all the way to, I guess I put the line there, for 248 till 489. So if you go to 248, here we go. Then you can comment out whatever information you have as temp pushback and pretty much not generate those. For example, if I don't want to generate, this is the grain ID, I can just comment it out. If I just don't want this, I comment it out. So you can comment out all of them and add whatever you want. But then you need to recompile it. So don't forget about it. If you change this source file to get the quadrature output you want, then you need to recompile the code. This is like kind of like a more advanced feature, but I want to mention it here because it's very useful. So you most probably have to do it just once because there is a certain number of variables you want to do. So you do it once, recompile it, and you're all set. So let's go back here. So we are done. So the target release is ready. So I can do actually all of this that I opened with atom I here. So if you actually use vim prm.prm, oh, first we need to go to that folder. So FCC, then FCC random orientation block. And then this is all the parameters input file that I have here. No, sorry. I can go back there. Yep, here. So this is the same file. This set is the same as this. So you can open it either way. Or in Ubuntu, actually, you can go to the folder and open it there. For example, let me see if I can bring this up. Okay. If I can open, this is the input file here. So it's pretty much the same as the atom editor that I have. So, and also you can open the source file. I give this address in the handout. So you can open this also and go to line 248. This is pretty much the same as you can see here in the atom editor. So it doesn't matter. So you can actually change that. For example, this 3 will provide for you the X, Y, and Z of the quadrature point. And the last feature I want to talk about is tabular output. What if you don't want to print out every 100 increments, the output? What if you just want to print out the output at a certain time? For example, in this case, at time 0.25 and 0.48, then you just put set tabular output equal to true, and then define those times you're interested in. And those outputs will be generated just at these times. So besides the quadrature output and the output for Paraview, which has a contour plot, as I mentioned, stress strain.txt is always generated. So you cannot disable that one. It's just a macro response that you can actually use it for calibration pretty much. After that, it's the boundary condition parameters. So there are different type of boundary condition you can cover using PRISMS-Plasticity. Simple boundary condition, it's like you just linearly increase the boundary condition, a specific boundary condition until you reach a final value. That's simple boundary condition. Also, you can apply velocity gradient tensor on the sample. For example, you can apply a rolling deformation gradient on the sample. Then you can have cyclic. Also, you can have tabular boundary conditions. So you can see that, for example, from time 0 to 1, you're applying compression. Then from 1 to 2, you change the direction of loading, so on and so forth. There is a pipeline for SEM-DIC that you can actually read in the boundary condition from an SEM-DIC experiment, and you can apply it on the sample. And finally, periodic boundary condition. So 3 of them I'm going to cover today, which are simple boundary condition, velocity gradient tensor, and tabular boundary condition. And periodic boundary condition, hopefully I'll cover it tomorrow on session number 2. So for simple boundary condition, you have set use simple boundary condition equal to true. And then there is a file, boundary condition info.txt. Then you need to define how many lines of header it has. It's usually 2. And number of boundary condition you're applied on the sample. So this is the boundary condition that if you open actually the boundary condition, this is the file you'll see. So it's pretty much what I have in the handout. So there are 3 columns. The first one, okay, there are 3 columns. The first one defines what phase you're applying the boundary condition. The second one defines in each phase what degrees of freedom you're applying. The third one is defining the boundary condition that you're applying at the final time, like when the time is equal to the time total, what boundary condition will be applied. In this specific file, we are holding phase 1, which is in this phase, in the X, Y, and Z direction. And when the final deformation is 0, it means you fix it throughout the simulation. So you have fixed boundary condition on this phase. And then on phase 2, on direction of 1, you're applying, direction of 1 is X. You're applying minus 0.5%. So you're applying compression. And since the sample size is 1, it's equal to 5% compression. Okay, so velocity gradient tensor, first you need to use this feature, set use simple boundary condition as false to just let the software know that it's not going to be a simple boundary condition. Then you're going to set use velocity gradient boundary condition as true, and then apply your velocity gradient to the sample. The next one will be tabular boundary condition. So within the tabular boundary condition, first, again, you need to use set use simple boundary condition as false, set use tabular boundary condition as true, and then import your boundary condition, the file of it. And then the difference with the simple boundary condition is you need to define how many boundary condition during the time you're going to define. For example, in my case, if I start from 0 to 1, 1 to 2, and 2 to 3, I will end up with 4, 0, 1, 3, 0, 1, 2, 3. So 4 data for that tabular boundary condition. It includes the initial boundary condition. So for example, in this case, I have 1, 2, 3, 4, 5 boundary conditions, which I define here. And then this is the timetable. So from time 0, 5, 15, 25, 30. And this is how the file would look like. There is no header for boundary condition info table.txt. So this is the boundary condition that I'm applying right now on this direction. And the other 3 directions are all 0. It means I fix those directions. I just apply compression and then tension and then compression and 0 on the 6th phase in the Z direction, which is this one, on the Z direction, which is going to be simple compression. The solver parameter is the next important part of the code. So this is very important. You need to define what is the time step, what is the total time, linear solver iteration, relative linear solver tolerance, and maximum number of linear iterations. But what are these? The first one, time increment. So there is a tricky part. So for time increment, it depends on the total applied strain and the total time. So for a set of material system and loading boundary condition, you need to first actually optimize this delta t for your problem. What I will do usually is I start with the number of 10 to the power minus 4 for the strain applied within each increment. So how can I define that? Let's assume you're applying 5% strain at the total time of 1. Then the time step, so let me open a notepad. So let's assume you're applying 5% strain and the total time is 1. Okay, what we want to do as a starting delta t is we want to have 10 to the power minus 4 as a strain increment. So the total strain is 5%. So if you pick delta t equal to 0.05, then your applied strain within each increment will be 5%, which is 0.05, times the time step. Oh, so it's actually this, times the time step, which is this, divided by the total time. So this will become 10 to the power minus 2 times 10 to the power minus 3 is 10 to the power minus 5 times 10 is 10 to the power minus 4. So this is a good starting point. So for this specific problem. Now, if you do the simulation, your initial simulation, and it diverges, then you need to divide this by a factor of 2. So the next delta t will be, now if it actually converges with delta t equal to 0.02, you can actually multiply that by 2, which I rarely see the case that it actually get larger for the material of FCC copper. So you might have a material system, you will end up with the larger delta t. So in that case, you will use the second guess as this. So that's pretty much how you can optimize your delta t through the simulation. After you figure out your golden number for delta t, then you can use that throughout the simulation. Okay, so the next important parameter is these two. Since we are using a very large systems in FE code, we are typically using iterative, some iterations to inverse the problem. So it's an iterative operation to find the inverse problem or solve the linear equation. For that, the default engine for solving the linear equation is by CG method. And for that, you need to define the maximum number of iteration it will go through and the relative linear solver tolerance. So if the code find the error and is smaller than this number times the L2 norm of force vector that you have, then what will happen is it will stop and it says that, okay, the simulation, the solution of linear equation is reached. So if you have a very, very small linear solver tolerance, then it will take more time to reach. But be careful, if you really choose a large value, you might find the solution really fast, but your simulation will quickly diverge after a few increments because that's not actually the true solution of that linear equation. You just artificially increase the criteria or loosen up the criteria to get the convergence, which is not correct. And the final part of the code that I'm going to explain is the input microstructure. So this part, you can see it defines the number of voxel in X, Y, and Z. In this case, each grain is modeled with one element. So you can see in the FE mesh we had, the number of element was 5 by 8 by 10. So we use the same input microstructure. So each grain can be modeled by one FE element, which is, so the grain ID will be 5 by 8 by 10. And I use the number of header equal to 1. And finally, you define the orientation file and grain ID file. So that's pretty much the main part of the code. There is another input file that it depends on material model. For the default material model we have in Prisms, we have rate independent model. So that's how rate independent model look like. We have multiplicative decomposition of deformation gradient to deformation gradient elastic and plastic. And then the key idea of crystal plasticity is to link this LP, which is plasticity velocity gradient, to the activation of slip system on each direction. And then in the rate independent model, each of the slip system has its own yield function, which needs to be satisfied. And this is the evolution of a slip resistance, which has the initial hardening, the saturation value, and the exponent value. So if you have so as you harden the material, the hardening parameter, which H alpha beta, it will drop. Also, you will have the Q parameter, which is latent hardening parameter for each slip system. That need to be defined by matrix, which is defined in the file here. So this is actually defining. So this is that matrix. So if you have 12 slip system, you'll end up with 12 by 12 latent hardening matrix. For example, in the case of FCC, we know that basal are coplanar. So we have the basal 3 for each of those, which has in the same plane, which are 3 slip system, we use 1. And then if they're not on the same plane, we use 1.4 for copper. So this is the basic rate independent model. So these are the information you will have in the input file. So the first one is elastic modulus, row 1 to row 6. Then you have the number of slip system, in our case 12 for copper. Then that file, which has the latent hardening ratios as a matrix, 12 by 12. And then you have initial slip resistance. When you don't have any plasticity, that's the initial slip resistance S0. And then this is the initial hardening module you have here as H0. And then you will have the power law exponent, which is this, A beta. And then you have saturation stress for each slip system, which is this SS. And then the name of the slip direction and slip normal. So if you open the slip direction and slip normal, that include the information for a slip direction and a slip normal, which for FCC, you'll end up with this for a slip direction and this for a slip normal. Okay. Now we have covered all the main input files. So we're almost ready to do the simulation, the first simulation that we're gonna do. So I think that's a good time to answer any question if. Okay. The question is, oh, okay. So Dream 3D on the Linux system. Okay, let me.
Here is up.
Hey, yeah. I will go over the Dream 3D for the Linux system. So
I think a problem solved. Yeah. Like
okay.
We were just chatting separately. I think.
Okay.
The participant was able to figure it out. Yeah.
Okay. So I just wanna showcase it in case anyone is interested. Let me open a Ubuntu machine. Okay. So this is a Kane machine that we actually connected to, and this is an fully Ubuntu system, not a Windows subsystem. So what you will have is you can download the Dream 3D package from the link that I provided and extract it. And then if you go to this folder, and if you go to Bean, double click on Dream 3D, it will open the pipeline. I'm gonna quickly open. So if you go to the training session, plasticity, training material, pre-processing, HCP, pipeline, open it. And then you need to update the address, pretty much the same. And then update this the address. And then update this address as well. Oh. Okay. So this will be this copper. Okay. And then you can actually start the pipeline. Oh, I forgot to check how many grain ID we'll have. So you go to this and see the estimate number. In this case, 317, and then generate it. It will be the same. So it's very close to what I just showed. Okay, close without saving. So let me close this Ubuntu. And then there was another question. Okay, how are basal, prismatic, pyramidal, C+E arranged, ordered in the sleep direction? So whatever, if you have any preferred order, whatever you order here and here, you need to keep the same order for this. For example, if you go to HCP plasticity and you go to application of HCP materials, then open the parameter input file, you can see that the first three we usually go with basal, then we have prismatic, then we have pyramidal A and pyramidal A plus C. But how can we dictate this? By going actually, if you open the direction, you can see the first three are basal, then prismatic, then pyramidal A, then pyramidal A plus C. This is how we manage the order. So whatever order you have in a sleep direction, normal or tween, you keep the same order in input file. I hope it answers the psi question. Okay, any suggestion to set boundary condition for a nano indentation study? So for nano indentation study, if you go to deal 2, there is an application to apply contact. So for that, you can actually use the contact application for that. But another easier maybe would be to get the deformation predefined and then trick the code to apply the same predefined deformation to the nano indentation. But I've never done that personally. I can think about it and come up with a better answer. But that's a very good question. So these are the question. Okay. Okay, sure. This is done. Where do we define tweening directives? So that actually I wanted to go for tomorrow's session, but I can quickly show here how it works. So if you open a parameter input file regarding one of the tweening applications, like this one, if you go, there is another added set of data in the input file. So you need to set the tweening enable true and then define the information for tuning. And then you define the name here. It's pretty simple, not much. It's you just follow one of the examples in the HCP and substitute the information. Okay, sure. So, okay. So one more question, maybe if we have any, otherwise I'll go over doing the real simulation. Okay, so let's go over the simulations. So for that, let me see the handout first. We are doing the FCC random orientation block as a first example. So I tried my best to have all the commands you required there. So hopefully we can follow there, and feel free to use any text editor you're comfortable with. So we can edit the text as recommended in the handout. So first, these are the files. Let's open the parameter using VIM command. And then going to line 52, and then make the output true. And then make the skip output every 25 increments. What else do we need to change? Okay, everything is okay. So we are just clicking on the escape, semicolon, W, Q. We are good. So the next part is the boundary condition. So you can see what type of boundary condition we are applying for this problem. This is applying the symmetric boundary condition. So symmetric boundary condition is actually what we have as we are applying on each face, we are fixing it, and then apply compression in this face number 6 in the Z direction and 5% compression. And you can see the increment we are using, the strain increment we are using is half of what I start with. So the command you need to run this simulation now is MPI run -n. So this is the command that we need to do. MPI run -n6 main PRM. I'm using 6 processors. You can use whatever number of processors you feel comfortable with your system. And we'll wait for about 50 increments, so at least we get 2 output ready for us. Okay, let me see what questions do we have. Yep, that's true. So for this specific simulation, every grain is modeled using an FE element. This is actually a real simulation we published for texture evolution use case of PRISMS-Plasticity in our paper. So it's pretty the same application. So you can use this as to check the results we have published back in 2019. And the target was not getting the correct macrostructural stress strain. The target was getting the texture and change it and see how it goes. But there are other simulations I'll go tomorrow that you'll get actually the real application from a real eBSD data, and you model that and you get the each grain then maybe possibly modeled with hundreds of elements. Or can I fix a nano indentation example somewhere to follow using PRISMS-Plasticity? I think it's doable, but we need to, I've never done it personally. So it's something we can definitely work on it together. I'm also interested to see how it's applied. We never has done nano indentation experiments, so it was never our interest to do it. But I can definitely work with you to implement that into the code. It shouldn't be that hard because it has been already something close to that implemented in DIL2 examples for general FE. Can you explain a little bit more on contact conditions and interface of composites? So there is no contact in this specific example. Oh, let me close. Oh, for contact, I can give you some detail. Let me close this. Okay. Okay. So I'll answer that in the next waiting moment. Okay. So we have, or Adi, if you know, you can answer that question. That would be great. So we have now a folder results here. So if you go to the folder results, you can see some interesting output provided here. So the first one that catch my eyes is stress_strain.txt. This is the file that I was talking about. This is the homogenized response of the sample. And excuse me, you can use the this output for the calibration exactly. And the rest, there are two types of family. So this projected fields and solution. Solution is nodal displacement. It's actually the direct solution of linear equation KU equal to F find element. And it's a nodal displacement, so it's direct because Paraview needs the nodal information for post-processing. So it's directly transformed to Paraview. For other variables, which are calculated and obtained at the level of integration point, you don't have the nodal information. Then you need to project back using the solving an inverse linear equation to extrapolate the information from integration point to the nodal point. For example, to get the stress, strain, all the information. Those are projected fields. You can see there are a few VTU files, which I use 6 processors. It starts with 0, it ends with 5, sorry. So it's in total 6. So this is like a share of each processors for the output. And this PVTU file is the file that you actually open in Paraview, which gather all those information and link them together. So let me go back to the handout. So we need, what we need to do is now to open Paraview. Okay, here is a Paraview. I just delete whatever I had. I open the file. I go to the test folder I just made, applications, crystal plasticity, FCC, and we did FCC random orientation block results, and I will open projected fields and click on apply. So change the solid color to whatever variable you want, like equivalent strain. And then you can change it to surface with edges. So then you can do all the stuff you want using that. You can do different color map. For example, different color maps, different plot radius. You can apply threshold to get the data. You can get some data here. So these are all information. For example, this is equivalent strain. And you can also march through the steps. So let me make this smaller. Okay. So you can actually march. We killed it at 80. So we had 3 output. So it's the first one, the second one. Then you need to rescale it automatically. And then this is the third one. So this is, you can actually go here, and this is equivalent stress. The equivalent stress, the maximum stress we have is 96 megapascal for now. The units are all in megapascal. Within the input file also, all the units are in megapascal. The next file that you can open is, oh, sorry. This is file, open, solution. So you can go file, open, solution, and then apply. Then you can get U, and then you have the Z direction. So you can see on one edge, you have 0. On the other edge, you have negative, which is a compression. Something interesting is you can actually get the deformed shape as well. So if you go to filters, alphabetical, and you go to wrap by vector, and then click on apply, then you can change the scaling. Like you can change the scale to, where was that? Here, to 50, because the deformation we applied was really small. You need to scale it. You can see it now. 50 is a little bit too much, maybe 10. Yep, now you can, oh no, it's actually 50 was good. It was for the last step. Then you can march back. So this is pretty much, and you can get the information, and this is the deformed finite element meshes. So you can get all the information again out of this. So what else do we need? Okay, now that you know all this visualization features, so be careful. Whatever we have here, for example, for project field, you can get it. You can add other variables of interest for yourself within the code. I'm trying to cover that part in tomorrow's session, so stay tuned on that one. So let me see if there is any. Can we show grains here? Yep, we can show grains. So you can click on grain ID. And this is actually each element one grain. So this is like something like this. This is a synthetic microstructure. Okay, so something is, if you are trying to do the simulation, but it gives you a warning, not enough slots, it means maybe you are using too much number of, so your system is too powerful. So bring down the number of processors you are using and it may work. For example, if I use $10, it says not enough slot. So, or you are using, if your system is like 7 processors, you should usually basically use 4 or 5 or 6. So please try only 2, 3, or 4 and see if it works or not. I hope it helps you. Does the framework account for type 2 residual stress? No, but we have finished a model that it actually accounts for residual stresses, and you can just add it to the model. But a simple solution for that is, you remember the orientation file I was talking about? You can add a column to the orientation file and define your residual stresses, and then as an eigenstrain, and then relax the sample without applying extra boundary condition. Just fix it just to not move it around with the residual stress. Do the relaxation phase and start your real simulation after that. So then you can actually account for residual stress. And for boundary condition setup for contacts that I didn't respond earlier, you can define linear constraints between any nodes of your interest. So that's a little bit of advanced feature. So maybe we can talk offline. If you can send me an email, I can show you how you can define those contacts. Okay. So let me, as an side, I wasn't okay. So I can show simulating one of the larger sample and show how the grain IDs look like then, but that's also interesting question. So the next step is, after you got this done, let's plot the, okay, let's plot the stress strain. So if you go over your results, so you can use either Ubuntu, you can either use Ubuntu LibreOffice Calc for that, or Excel. So I'm using right now Excel for this. So I will open with, okay, so I will use Excel here. And I copy the address and I just open it here. So you need to change all Excel files to all files and then pick stress strain. And then this box, text import wizard, will come up. Then you can just click on finish. So now you have the Excel file. So what you can do easily is you can just click on the column C, stay on, keep pushing the control button, and then click on the column I, and then insert, scatter. This is gonna be your stress strain. Oh, sorry. So you can move this. So this you can use for the calibration. If you are using the, oh, this one is, oh yeah. If you are using, okay, let me find the Office. So you can use LibreOffice Calc for Ubuntu system. Nope. So hopefully that will come up. Maybe I should just click on yes. Discard, yes. Okay. Now I will open one of my recent documents. Hopefully it has it. Now you just need to click on OK, open, and go again, column C and column I, and insert, chart, go on scatter, finish. This was another sample, like a cyclic loading, so that's different. I just want to show how you can plot using LibreOffice Calc. So this is how you can use Ubuntu to plot this stress strain curve. Okay, so for this, you can pretty much have all the information. So something to play with for the next session, and you can come and ask question, is these are kind of like your homeworks for the next session. Change the loading to uniaxial tension. Here you go. Change the loading to uniaxial tension. Use a more refined mesh. Output quadrature output and investigate the output file. So you can actually modify this update after increment, recompile it, and just print out some specific information that you want. For example, you can just output grain ID, position, and orientation. And I made some guideline on this one. And the last one, applying a cyclic loading using the tabular boundary condition. So I pretty much went over all of these features, so you can use the handout. So this will be covered by me at the start of the session too, very quickly. But if you have any comments or questions, you can shoot me an email regarding these homeworks for tomorrow. So this will be your homework for tomorrow. But for the next step, what I will do is I will go back to one of the samples with external mesh. like simple tension with external mesh. Here we go. Oh, sorry. Oh, my bad. Let me close it. Okay. So I need to go again to my folder. Okay. Test, plasticity, application, crystal plasticity, FCC. So this will be simple tension external mesh. So you can go to simple tension external mesh. Now, if you open the input files and then open the prm.prm, we're not gonna, this is actually a kind of heavy simulation. I'm just gonna show you how the post-processing results look like. So I make the write output true, and I make it every increment. Then I will kill it after 1 or 2 increments just to post-process the results. So it will be MPI run. So let me do that again so you can follow. So what I did was I take this switch write output to true, and I make the skip output step to 1. So it's MPI run and 6 processors in my case. In your case, it might be 2, 4, 8, whatever. Main. So I kill it after just 1 iteration because it has been already generated the result I want. So this is file open. Now I can go over the simple tension external mesh results, projected field PVTU. Yeah, that was also another. So this is a part of a large microstructure. This is the one with the unstructured hex that I just simulated. I thought it had a problem. It didn't. It's just a section of a very large microstructure. So it doesn't have like 1,000,000 grains. It has. It just want to show how unstructured hex mesh can be generated and simulated. Okay, so by this. This is pretty much all we would love to cover in the first session. So you, as I mentioned, you have this small homework to do, and feel free to go over the code and do any of the applications. And we're gonna stay here for your questions. If you have any specific application you have in mind and you want to see how you can handle that, or if you have any question regarding any part of the code or any part of the training, you can ask right now.